Okay, I guess yesterday's didn't go very well. So yesterday I got an introduction from, director of Cal IT2, from Alon, and today I get to introduce myself. So, okay, fine, we go on anyway. So Alon, wait till next time you ask me to do something, huh? Okay, so what I want to do today, so one can think of yesterday as sort of laying the groundwork on the fundamentals of wireless communication. Today we're going to build on the groundwork, but add on top of that information theoretic thinking and explore new ways of communicating over wireless channel. So it's interesting to compare and contrast sort of the two approaches. They sort of provide different point of view. So to do that, I have to lay the groundwork by saying a few words about capacity of wireless channels. So I'll spend about hopefully 45 minutes or so doing that. We'll take a short break, and then we'll talk about two topics. One, opportunistic communication, and number two, MIMO. And that should finish up the short course. Okay, so information theory. The contrast with yesterday is, if you think about what we did yesterday, we were looking at specific schemes, specific communication schemes, and analyze their performance to get some insight as to what's going on. So today we're going to do it in a more systematic fashion. We're going to look at fundamental limit, and of course information theory, as we all know, ITA provides sort of fundamental limits to any communication problem, in particular the wireless communication problem. Now, different people use information theory in a different way. Some people use it for fun. Some people use it to derive bounds on how good codes can perform. So I use it in a slightly different way. I use it in two ways. One, I use it to identify the impact of channel resources on performance. So capacity formulas to me gives a very simple way of understanding. For example, if you increase power, if you increase the bandwidth, how much impact does that have on your performance? Much simpler than looking at very detailed specific scheme. And two is that it suggests new ways to communicate over the wireless channel. So if you look at the wireless problem, and then you take an engineering point of view to that problem, and you derive some scheme. What information theory tells you is, hey, you know what? If you look at the problem more fundamentally from scratch, without any bias, prior bias, then there may be new ideas come through. And that's essentially what information theory did for wireless in the past 10 years. And I want to tell a few stories about that. So essentially, we're talking about modern wireless communication today. Okay, so some historic perspective. Wireless communication has been around for a long, long time. Marconi invented wireless communication 100 years ago. Since then, lots of very smart engineers have worked on wireless communication systems. We talked about some of the techniques developed yesterday, like Alamuti and so forth. These are very ingenious, but somewhat ad hoc design techniques. What we bring in the table is a development started by the other guy, Shannon. In 1948, he wrote this astounding paper, which essentially says one key thing, out of many things he said, but there was one very key thing that he said, is that every channel has a very definitive notion of capacity. It's like a pipe, and the pipe has a size, and that size one can calculate given the statistics of the channel. So what has happened in wireless communication in the past 10 years is really people have been applying this framework of thinking on essentially better understanding of wireless channel capacity. And the advances, MIMO, opportunistic communication, are essentially all built on top of that. So we're going to talk about the new points of view. A very specific point of view that we'll advocate is the view of the fading channel. So again, we come back to our fading channel, which has been our object of obsessive interest. There's interesting echo. I hope this is not going to affect your taping of the session. Do you guys hear echo, or are you okay? Yeah, okay, all right. So we go back to our object of interest, the multipath wireless channel. And we saw this crazy figure here. The channel is going up like 1620 dB. The view that we took yesterday, in fact, the view that was taken since Marconi times, really, is the view that, the fading channel is really very unreliable. It's really very unreliable. And if you want to communicate reliably, you have to try to compensate for the unreliability. Okay? More important view is the other way around. It's saying that, the fact that the channel behaves like that actually provides opportunities to exploit, to increase spatial efficiency. Okay? So this is the shift of point of view. And to really start talking about these notions, I really have to introduce some basic capacity concepts. I don't say basic information theory concept, but I say basic capacity concept because I really don't go to the detail level of information theory, but I really just give you a few formulas about basic channel capacities, and we go on from there. Okay? So we take it as a given, this formula. This formula, a lot of people should know about. This is ITA, presumably there are information theory courses here. And capacity of the AWGN channel, our baseline channel, is given by this formula, log 1 plus signal-to-noise ratio, bits per second per hertz. So it's equal to W, the bandwidth, times log of 1 plus signal-to-noise ratio. So this formula is quite nice because it exactly identifies the impact of the resource on the performance. So if you think of performance as a capacity, then it tells you that the capacity is linear in the bandwidth for a fixed signal-to-noise ratio per degree of freedom, and logarithmic in 1 plus signal-to-noise ratio. Okay? So, and then if we want to get back to units of bits per second in terms of the transmit power constraint, so if the transmit power constraint is p watts, the noise spectrum is n naught, then the SNR is just the transmit power divided by the noise power, which is n naught watts per hertz, times the bandwidth, and we get SNR. And this is the formula, the famous Shannon formula for AWGN capacity. So we will look at this formula and play around with it a little bit here. We record this formula again. So basically, from this formula, you can identify two regimes of communication. And most communication systems are essentially more or less can be categorized into one of the two regimes. So it's very important that when we think about communication system, we figure out what regime we are operating at, because it depends on that. The optimal communication schemes could be very, very different, okay? And the behavior could be very different. And the impact on the resource of the performance can be very different. So number one regime is the so-called bandwidth limited regime. So in this regime, basically, the signal-to-noise ratio is much larger than 0 dB, okay? So in this regime, the capacity is essentially logarithmic in the power, because if this is large, you can ignore the 1, and you can think of this as logarithmic in the power, and approximately linear in the bandwidth. Why is that? Because if this is high, then if I increase the bandwidth, this will decrease a little bit, but I'm at the high SNR regime, and so it's not sensitive to the SNR. So the picture that you should have in mind, actually, there's only one picture you should have in mind to understand all this, is the fact that if I plot the capacity formula, log of 1 plus SNR, then this is a concave function, so that when you're dealing with high SNR, the performance is not very sensitive to your SNR because of the concave nature of the curve. Okay? So this is the bandwidth limited regime above this point. And then here, the capacity is not very sensitive in the SNR. So when you change the bandwidth, okay, the capacity in terms of capacity bits per second per degree of freedom, this log term doesn't change a whole lot, but it changes a whole lot in the W because it's linear. So at high SNR, you're roughly linear in the bandwidth. Yeah?
Can you say why you're using transmit power in your capacity?
Oh, did I say transmit power? Yes, I guess I've normalized the channel, so maybe I should say receive power. Yeah, what I meant is receive power. Mistake. Typo. Okay. But you can always, in an AWGN channel, you can always translate transmit power, receive power by scaling factor, which is a channel gain. Okay. All right. This is the bandwidth limited regime. So why is it called a bandwidth limited regime? That means that in this regime, if I increase the bandwidth, the performance increases a lot. If I increase the power, the performance does not increase a whole lot. So suppose I give you 3 dB extra power, okay? 3 dB extra power will only give me 1 additional bits per second per hertz, 1 additional bits. Whereas if I double the bandwidth, I double the rate, okay? So if your rate is, if your bits per second per hertz is about 5 bits per second per hertz, if I double the bandwidth, I get 10 bits per second per hertz. 10 bits per second, I should say double. And if I add 1 more bit, it's only 20% improvement. Okay? So the second regime is the opposite. This is the bandwidth limited, this is the power limited regime. So in this regime, the signal to noise ratio is small now, much less than 0 dB, okay? So in this regime, you can see from this curve that we're now here. And at this point, the capacity is more or less linear in the signal to noise ratio, and therefore linear in the power, okay? Capacity is linear in the power. So if I now double the power, 3 dB more power, I now double the bits per second per hertz, as opposed to adding only 20%. Okay? What about the bandwidth? If I look at the bandwidth, then because this is linear in the numerator, in the argument, so log 1 plus x is roughly equal to x, the bandwidth cancels, and therefore the capacity in this power limited regime is insensitive to the bandwidth. So here, like in an ultra wideband system, if I give you 500 megahertz, you get a certain performance. If I give you 1 gigahertz, keeping the total transmit power the same, your capacity hardly increases. Okay? So that's why it's called power limited, but not bandwidth limited. On the other hand, if I give you extra 3 dB, you can double your spectral efficiency. Okay, so you can plot this curve, famous curve. If I plot for fixed transmit power, as a function of the bandwidth, in a bandwidth limited regime, you get a sharp increase in performance. In the power limited regime, it saturates at, you can calculate this, P over N naught times log 2E. So in this regime, if I increase the power by 3 dB, this limit doubles. Okay, so we can see that here. All right? Yeah, if there are any questions, please do ask me. Okay, so this is the simple AWGN channel. Let's look at a little bit more complicated channel. And let's look at a frequency-selective channel. Okay? So in this channel, we have talked about that yesterday. The channel is time invariant, but the coherence bandwidth is smaller than the actual communication bandwidth. So you see multiple taps here. Okay? I assume people remember what happened yesterday, so I'm not going to go back to that again. This is multiple tap, LTI channel. Therefore, it's frequency selective. What's the capacity of this channel? Okay? We can apply information theory to study that. Shannon studied this problem very, very early on. And we can use our technology. And to study the capacity of this channel. And the technology is OFDM. Okay? So remember, what does OFDM do? OFDM basically converts this channel to a bunch of subchannels or subcarriers, parallel, each of which do not interfere with each other. Okay? Remember, NC is the number of subcarriers. Okay? So in the OFDM, you can choose NC. Since this is a time invariant channel, so we can choose NC to be arbitrarily large, so that the overhead with the cyclic prefix is negligible. So we can think of this essentially as giving equivalent capacity to this channel. Okay? So now, how do I communicate over this channel? Well, each of these guys are just a scale version of the AWGN channel. So if I decide to put a power Pn into subchannel n, then the capacity per bits per second per hertz on each of these subchannel is given by log 1 plus the signal to noise ratio, receive signal noise ratio, at that subcarrier. And this is equal to the transmit power times the channel gain divided by the noise on that subcarrier. Okay? You sum that all up, you get the total capacity of the system. And now you ask, well, I have a degree of freedom here because I can choose my powers. Yeah? Yes? Okay, so I went through very quickly, right? OFDM is an invertible transformation. Remember the block. IDFT, DFT. These are invertible transformations, so you don't lose any information. So therefore, whatever achieved capacity in the original channel, achieved capacity OFDM. The only trick is that you add a cyclic prefix, and that wasted a little bit bits. But if we assume NC is very large, then that can be ignored. I don't quite understand the question because, so you're saying that OFDM may not achieve capacity, you worry about that? But you agree that whatever I transmit in the OFDM system, whatever I transmit in the original channel, they can be reconstructed from each other. Because the processing is through this inverse DFT and DFT, right? These are invertible transformation. So I don't lose any information. So whatever achieved capacity before, achieved capacity now. That's what I'm saying. And I know how to achieve capacity for this channel because it's a bunch of parallel channels. Okay? All right, good. So it turns out that you can solve this problem. So now the problem is the following. The problem is I allocate different power on each of the subchannel, and I want to optimize this expression. Okay? And you can see a picture here. Okay? So the optimal power allocation is given by this famous picture called Waterfilling. So the picture is the following. I plot as a function of the subcarrier the channel response, the frequency response, that is the size of the tab, the size of the gain of various coefficients. Okay, the reciprocal of that. So this is the plot. So that means the smaller this contour is, the stronger the subcarrier is. It's inverse proportion of that. So I allocate power in such a way that I have a total amount of power I pour into this vessel. The power allocated in each of the subcarrier is precisely the difference between this water level and the bottom of the vessel. Okay? So therefore, this strategy makes some sense because what this strategy is saying is the following. If you have a bunch of subchannels, okay, and I have a total amount of power budget, then I want to use my power quite carefully. Okay? In particular, I want to use more power on the subchannel, that will give me more bang for the buck. And those are the better subchannels. So therefore, if the channel is better, then I put more power. Okay? If the channel is not so good, I put less power. If the channel is really bad, then I don't put any power. Okay? Now, all right, everyone understands that, hopefully. Let me ask you a question, since I got some questions from the floor, so I'm now going to ask you a question. So every question I get from the floor, I'll ask one question, right? So that's how it works. If I follow this logic, why don't I put all the power in the best subchannel? Why don't I put all the power in the best subchannel, and then I'm done with it? This is connected to this picture. Hint, hint, this is connected to this picture. Sorry? That's right. So it's like maybe buffet or something, right? I use a buffet example. If I give you a lot of food, in the beginning when you're really hungry, you're very happy and you thank me. But now you're getting really full, and any more amount of food, you say, you know, just give me something else. I don't want food anymore. Give me money or something, you know. So that's what happens. If you give more power to a carrier, after a while, it becomes not very useful, and you move on to another subcarrier. Okay? So yeah. The bandwidth, of course, will affect the number of subcarriers. Okay? So basically, there's a scaling here, which is the number of subcarriers. What is this? This is sum of the capacity. Don't worry, it'll work out fine. It'll work out fine. So at the end of the day, when you take appropriate limits, then it'll work out fine. I see. So this is the capacity of this system, but this is happening over NC symbols. So I divide this by NC to get back the rate. Look, I can't figure out a normalizing factor in front of like 100 people, so don't worry, it'll work out fine. Okay. But it's of course proportional to the, of course, it's a function of the bandwidth you have at the end of the day. Okay, so this is the first application of this log formula. Okay, the application is that now I don't want to put all the power in one subcarrier. Okay, I want to sort of equalize them. All right, so now we're ready to go to our favorite fading channels, and now we can use the capacity formulas to give some insight as to what's going on. I'll consider 3 different cases, 3 different situations. One, I will first go back to the slow fading channel that we talked about yesterday, and I will define a notion of outage capacity. Then I'll go to the fast fading channel, and I'll define another notion of capacity called the fast fading capacity or the ergodic capacity. So we never use this word ergodic capacity in our book because we figured we want to sell the books to many, many people, right? Hey, by the way, did anyone like go off to Amazon last night and order a book? See, I'm checking the ranking of my book every minute, right? Every hour. So I want to see a search of books. You know, normally I only get like 1 book a week, you know? So if 2 of you goes and actually ordered the book last night because of the lecture, then the ranking, you know, gone up by 10,000 or something could be. So it could be a very big impact. So that's low SNR. So I'm operating the low SNR regime here. Okay. All right. By the way, these jokes, only engineers laugh at these jokes, you know. It's pretty sad. Okay. So ergodic capacity is the information theorist term for this. Engineers sound really strange, ergodic, so we don't use it in the book. But it's ergodic capacity in the sense that we are assuming interleaving here, infinitely deep interleaving. Number 3 is we will also show that the capacity is different whether the channel knowledge is known at the transmitter or not. Okay? So we talk about 3 cases. And the 3rd case leads up to this idea of opportunistic communication. So a slow fading channel is the same as the, look like the AWGN channel, except now I have a random fading gain H. Okay? So this is my random fading. And I'm assuming that H is random but constant. So what's the picture here? The picture here is that the fading is slow. All right. Can anyone tell me what slow fading means in this course? I'm waiting. That's right. Coherence time is bigger than the delay requirement. So what's the picture here? The picture here is that the channel is fading. Okay? The delay requirement is short. Okay, so this is that's called latency requirement to avoid confusing with the word delay, which was used in a different way. Okay? So this is my latency requirement. You can think of voice, maybe 50, 40 millisecond here. My fading coherence time is maybe a few hundred milliseconds. Okay? So the channel is more or less constant in this block. I have to essentially decode the information at the end of this time because I got to get the data to the application here. So therefore, what I model is that the channel is essentially random because it can be up and down, but it's constant within the whole block. Okay? And okay, so the problem here now is that there's really no definitive capacity. Because in some sense, the performance is a random variable. It's a function of H. If H is good, then the performance could be good. If H is bad, the performance is really bad. So in this situation, one can define a notion of outage capacity, and that's an important concept. And the outage capacity is the following. So the outage capacity can be fit to any of the, and can be applied to bound the performance of many of the schemes that we talked about yesterday. Basically, the idea is the following. You go for a target rate R. So suppose you're doing BPSK, then it'll be 1 bits per second per hertz. QPSK will be 2 bits per second per hertz. So you fix that rate R. You hope to get that rate R reliably. If the channel capacity, in some sense, of the corresponding AWGN channel for that given edge, if that random variable now is less than R, so the channel can, you don't know what the channel is, so you're going to send at a certain rate. If the channel goes up and down, if the channel happens to be down, then you're out of luck, and you cannot reliably decode your bits. Okay? If it's above your target rate, then that means the channel is now strong enough, and if you do appropriate coding, then you know that you can reliably decode your bits. Okay? So this is the outage probability. So that's why we define a notion of outage probability. And the problem is that no matter how strong your code is, there will still be a chance that you're in outage because of the deep fade situation. Okay? So if I reverse that, then people call this the outage capacity. So in other words, if I now give you a target outage probability, say 10 to the minus 2, and you want to find the largest rate R such that your outage probability meets the requirement of 10 to the minus 2, then that's called the outage capacity. So let's plot some curve. So what's the picture here? If I look at, say, the Rayleigh fading channel, okay, then I can think of this pseudo capacity, random capacity, shall we say, as a random variable, and I plot the PDF of that, and I have a target rate R, and the area on the left of this curve, okay, is the probability of outage. And you can show that at high SNR, the outage probability by inverting, by explicit computation, will give you this formula, okay? So the first observation is that the outage probability also decays like 1 over SNR, exactly the same as the error probability of the uncoded BPSK or QPSK or whatever that we did yesterday. Okay? So, question for you, why didn't my outage increase even though I do a lot of coding now? My outage, in some sense, is still suffer this poor fate of decreasing with only 1 over SNR, as opposed to exponential or SNR to the power 20 or something. That's right. So the typical error was a deep fade yesterday, and that's the same event here. So I did not change the typical error event. What coding does for me is to avoid me from making errors due to the random Gaussian noise. But it did not be able to counteract the fact that when the channel is in deep fade, coding is useless because I'm coding over this whole block, and if the channel is in deep fade over the whole block, coding is not useful. And so there's the same outage event, same behavior with the SNR. Okay? And if we plot, for example, for a given outage probability of 0.1, what's the rate that you could get, what's the outage capacity you can get, and you plot that as a function of the SNR normalized to the AWGN capacity. So what I'm plotting now is in some sense to say, okay, if I give you an outage probability of 0.1, how much loss of the outage capacity with respect to the AWGN unfaded capacity for a given SNR, this shows you the loss. Okay? So the loss is quite dramatic. You only get low SNR 20%, high SNR 80%. If you go for a smaller outage probability requirement, you have to be more conservative in the choice of your rate, and this curve goes down even more. So typically, you lose a lot of performance, even if you do coding in a situation without any diversity. So a natural thing is to introduce some diversity. There are many different diversity schemes that one can diversity scenario that one can analyze in the book. So now today, I'm going to try to hard sell the book now. Yesterday, I was, laid back, very gentle. But today, going to start ramping up the marketing steps here. Okay, so in the book, there will be several different diversity scenarios I talk about. I'm just focused on the simple one here, receive diversity. You can plot a similar curve. So receive diversity is exactly the same formula, except that the effective channel is now changed from absolute value of h squared, the norm of h squared in the scalar channel, to the norm of the entire vector of the received channel. Everything's the same, except this is received. And you see a dramatic improvement. So this is, I think, the outage probability is fixed to be now 0.01, 1%. If you have no diversity, you have this curve from a previous slide. As you increase the amount of diversity, this curve goes up significantly. And you can see the dramatic gain from diversity now in terms of outage capacity. We saw that earlier, yesterday already, in terms of error probability of uncoded scheme. You get a parallel performance improvement in terms of outage capacity. Okay. So this reflects the diversity gain and power gain. Okay, so now we move on to the fast fading channel, which is essentially the main thing I want to focus on as we progress. So in a fast fading channel, we have the opposing situation. So here we have slow fading. The channel is constant over the whole block. Okay. In a fast fading scenario, we have this. The latency may be a few seconds, or maybe 1 second, and the channel varies a whole lot over this latency requirement. Okay? So now, I want to know what's the performance limit in communicating over this. So first of all, let's think about the operational way of communicating over this. You code the information, okay? And typically what you do is you interleave the information, the bits, so that different bits are sent over different times in this block. And each one of them will essentially see a different channel because the channel fluctuates so much. Okay? So, what is the performance limit of this channel? First question is, will there still be outage? So in the ideal case, where the latency is so long that you see a lot of channel realization, will there still be outage? No, right? There won't be any outage. Because outage is happening when you have 1 or 2 channels and it drops and you're dead. But now I have so many realization of channel that I can average over the realization of channel and I get a consistent performance. So now I can go back to the notion of capacity, go back to the notion of capacity, and now I can define notion of capacity for this fast fading channel. I don't have to go to the outage capacity anymore. Okay? So can anyone guess at the formula for the outage, for the capacity of this channel? We can guess that. Okay. So the way to think about it is the following. Okay. Suppose at time n, okay, at time n, the channel gain is h sub n. Okay. Let's call it h sub m. Consistent with the notation. At time m, the channel gain is h sub n. Then the amount of information, in some sense, that the channel allows me to go push through is log of 1 plus h sub m squared times the SNR. Okay? All right? This is what happens at time m. Now, if I just focus on this time, this is a random variable. Of course, the amount of information provided by the channel is a function of the channel at that time, and that's a random variable. Okay? Today, I feel like a rock star because I can't see anyone out there. The light is like right in front of my face here. Good, good. I'm getting to that status now. Okay. Even though I didn't even get an introduction this morning. Okay, so this is a random variable. So now how should I think about the fast fading capacity? Well, information is like a fluid. So I'm getting information, which is a random variable at different times. And if I code over a long duration, the total amount of information I get is what? Yeah, information should add, right? I mean, that's the sort of the basic thinking about information theory. Information should add. If I give you a little bit of information at this time, and I give you another information at this time, the total information you get, essentially, through this channel, is the sum. And that is essentially sort of the very consistent with sort of the Shannon thinking. The Shannon thinking is the following, right? You have a pipe. Channel provides a pipe to you. And the size of the pipe is the capacitance channel. So you can think of this as the AWGN picture. In this picture, the pipe is a bit funny because this pipe kind of changes in diameter. It's probably not very well made because it kind of changes in diameter at different times. So the diameter changes depending on whether the channel is good or bad. Okay? But the total flow rate is basically a function of the average of the pipe size. And that's essentially the picture that information theory gives us, and it's the right thing. So you basically sum over, say, m of these times, and that is essentially your capacity if you code over m of such symbols. So you can imagine you have a code word of length m symbols, you interleave it at different times, so that if the m symbol sees this channel and sees this performance, the average is the rate that you can pump through this pipe. And for large m, what happens? So now we apply some, I'm sure everyone has taken some random process probability course. I told people there's only one result that everyone should know about from probability, and that result is central limit theorem. Central limit theorem is too complicated for me. I want to go one level earlier. Law of large number. Law of large number says that this sum converges to the expectation of this, and that's the fast fading capacity. Okay? So if my advisor sees me explaining this concept this way, he'll probably just, what happened? All these things I taught you, and now you sort of reduce the level of drawing pipes and so forth. Okay. All right. It's my advisor. Uh-oh. Uh-oh. Actually, this is the right error code, too. It's strange. It's very strange. Okay. All right. So this is the capacity. And we contrast it with the outage situation. In the outage situation, okay, you have a random variable here. The mean of this random variable has no operational meaning. So if you give me this random variable, you tell me the mean, I don't care. Because what I care about is the tail, what happens around here. In a fast fading channel, the mean becomes important in its operational meaning in terms of the capacity of this channel. Okay? So of course, the latency, I'm assuming, to be much larger than the coherence time of the channel. This is a basic assumption. And if your application can have a tolerable latency which is large compared to coherence time, then this number is a meaningful number. You can hope to try to get close to this performance. Okay, so now we move on to the third capacity. So we have the outage capacity. We have the fast fading capacity. The capacity I derived implicitly was assuming that the receiver can measure the channel, but the transmitter cannot. So the transmitter, essentially in the earlier strategy, was transmitting at constant power. So every symbol he sends, he puts the same amount of power in there. And that's why this SNR, in some sense, is just the average power. And I put this in every symbol. So now I want to play some more games. And I want to say, hey, you know what? Since I am thinking about crazy ideas anyway, let's push it to the limit. So I think information theory is good because it's not free ourselves from any implementation issues, and we can dream on and push to the limit, and then write some papers and get tenure, and then don't have to worry about anything. And that's a good thing. And so we can dream on and say, let's not worry about the TD at DF issue. Suppose you have a lot of feedback and so forth. And you can assume transmitter knows the channel as well. So what's the capacity of this channel when the transmitter knows the channel? Okay? So now let's go back to this picture. Okay? So let's go back to this picture. Suppose now the transmitter is tracking the channel. So it knows when the channel is good, when the channel is bad, and so forth. Hey, we have already solved this problem. Where's the analog of this problem that we have solved? We haven't solved too many problems in this course. But there's a natural analogy of this problem. So what is this problem? At each time, I'm seeing a channel with channel strength HM, right? And I'm interested in the long-term performance, so I'm interested in sum. But now, I get to observe the channel state at the transmitter. So I know the channel strength at different times. How should we think of this problem? Well, one way to think about the problem is that we can think of it as our favorite parallel channel. So parallel channel is really a very fundamental notion in wireless communication. And this is an example of a parallel channel. We will see another example later on. This is a parallel channel where for each channel, for each time, it provides a sub-channel for you with channel strength H sub HM. Okay? So now what do you do? So now with parallel channel, we do water filling. Right? We do water filling. So the water filling picture is the following. It's the same picture as before. So now we're sort of actually applying a few insights that we learned yesterday, right? Yesterday, essentially what we saw was that time domain and frequency domain have a lot of mirror images to each other. So insights we gain in one domain, we can apply in another domain. And in fact, yesterday, we were applying time diversity schemes to frequency diversity situation. But now, we can turn things around. We apply what we learned in the frequency domain, which is water filling, onto the time domain. Okay, and that's what we're doing here. So we're plotting as a function of time my channel trajectory. Okay, all right. I'm plotting the reciprocal of the channel gain square, the reciprocal. So low means good channel. I allocate power in a water pouring way. Okay, so when the channel is bad, I allocate very little power or zero power. When the channel is very good, I allocate more power. Okay? All right? Okay. Okay. So first of all, I'm assuming full channel knowledge. So I am essentially pushing to the limit here, right? I'm assuming, what am I assuming? I'm assuming that the transmitter at time 0 already knows the entire trajectory forever. Future channel. This is obviously unattainable, but it is a bound to the performance limit. So the question is, do I really need that information to actually get this performance? What do I need? If you look at the power allocated at time 0, at time m, what I need is the channel gain at time m, which I can measure. And I need to know this lambda, which is the level of the water pouring, right? So if you think about lambda, what is lambda given by? Well, lambda is the water level. So what I want is essentially the level is such that the total amount of power I put in over time should be equal to the average power I have in my system. Okay? And that only depends on the statistics of the channel and not on the realization of the channel. So I can compute this. So fine. I can actually achieve this using only current and past knowledge. In fact, I don't even need to know past knowledge. I only need to know current knowledge and statistics of the channel, and I can achieve optimal performance. Okay? So in this formula, the capacity is the expectation Expectation, because there's a gain law of large number application, where the power constraint, where you have this is the power allocation, and lambda is chosen to satisfy the average power constraint. So the expectation of this over H should meet the power constraint. Okay? Very good. So man, we're good here. So we're able to derive the capacity with full CSI. So by the way, this is not a TV program here. This is CSI, stands for channel with side information. Full CSI means both the transmitter and the receiver knows the channel. Very good. So the performance, I can plot the curve. So let me explain what I'm plotting here. As a function of the signal to noise ratio, I'm plotting the capacity in terms of bits per second per hertz, free curve. First, okay, we have the AWGN curve. So this is the baseline, the AWGN curve. Second, which is the middle one, is the full CSI case. And the third one is CSIR. What is CSIR? CSIR means channel with side information only at the receiver. That is this formula, the expectation of log of 1 plus H squared SNR. And that's the lower curve. Okay? So let's see what's happening here. Just a sanity check to make sure I didn't plot anything wrong. The full CSI is always better or equal to the CSIR, which is good, right? More information, you don't lose performance. Good. However, we see that at moderate to high SNR, be above 10 dB or so, okay, you don't get much gain. The gap is very small. You lose a little bit compared to the AWGN capacity, but the two fading channel performance, whether you know the CSI at the transmitter or not, you don't get much gain. Why is that? Why is that? Okay, two things. One, what kind of gain do I get when I do this full CSI water pouring? So let's think about it, right? We have two fundamental resources in the channel. Degrees of freedom or bandwidth and power. Any good scheme that you come up with, in some sense, is a scheme that you can get either power gain or a degree of freedom gain, roughly speaking, or diversity gain. We're dealing with fast fading situation. So diversity is not an issue. Because I've already called over a long time, so I got infinite time diversity already. So diversity is out of the picture. Okay? So now we focus on the power gain or the degree of freedom gain. What kind of gain is Waterfilling giving us? Power gain, right? Because Waterfilling says that, I want to opportunistically transmit my power whenever the channel is good, so that the channel effectively is giving me a boost of my power. So I'm using the power effectively, so it's a power gain. Degrees of freedom is a fixed bandwidth, so I'm not really changing anything here. Okay? So it's a power gain. And first of all, at high SNR, power gain is not a whole lot useful. Because high SNR, I'm bandwidth limited, not power limited. Okay? So you're giving me something that is not very high impact already. However, you may expect maybe I'll get a 3 dB gain or something. Here, I don't even get a 3 dB gain. I get like 0 dB gain. Okay? So no gain at all. The difference is actually 0. You can show that. Okay? So there's no dB gain. By the way, when is there a dB gain? If I plot the two curves and there's a dB gain, do you understand how to read these pictures? So when the two curves are shifted by horizontal separation, then that's a power gain. That's a signature of a power gain. Because that tells me that if I increase my power by 3 dB, I get the same performance, like horizontal shift. So for example, there is a dB loss from the AWGN capacity. There's a power loss. But there's no power gain between these two approaches, two schemes. Full CSI does not give me any power gain at all, even. And the problem is the following. You can think of it this way. At high SNR, okay, what will happen to this picture? High SNR, you can think of, I have more and more power. Okay? So more and more power means what? I don't know how many floors is this building, but imagine this is now on Alon's office on the 4th floor. So now you have like huge amount of water on this vessel, And from a point of view of the height of this whole building, this going up and down business is minuscule. It's like a little, change of the floor height, whereas you have a huge amount of water. Okay? So compare that to allocating constant amount of power at all times. It's a minuscule difference. No difference. That's why there's no gain. Okay? All right. So now, however, at low SNR, what happens? Okay, so at low SNR, one thing bad about low SNR is that you can't see much because everything is going to 0. Now people say, geez, low SNR, everything goes 0, so what's the point, right? But don't worry. The fact it's going to 0 is the bits per second per hertz. But you still may be operating at a very large bandwidth. And so your aggregate rates can still be very high. So we're still very worried about what happens here. Okay? So for example, in the IS-95 system yesterday, the bits per second per hertz may be very low. But the total bandwidth is very large, so you have the processing gain, in other words. Okay? So, but at low SNR, we can't really compute things by plotting this way. What we can do, though, is we can normalize and compare ratios. So that's what I'm going to do. I'm going to normalize both these schemes, CSIR and full CSI, with respect to the AWGN capacity. So I want to see how much of the AWGN channel capacity can I achieve. Okay? So the black curve is CSIR. Okay? So first of all, it's always less than 1. That means you always lose a little bit due to fading. In the book, I explain how this can be done. I won't go into details here. But at low SNR, this approaches 1. The ratio approaches 1. Okay? So at low SNR, you don't lose much with only receiver CSI compared to the capacity of the AWGN channel. So fading does not provide any penalty to me at low SNR. In the fast fading scenario. Of course, outage-wise, it does. If you look at the CSIR, the full CSI, that means the water pouring strategy, we see something bizarre. So this is the first indication of something really weird going on. Okay? What do we see? We see two things. One, full CSI is better than CSIR. Hey, that's not surprising. That's not surprising because by definition it's better. Okay, so that's not surprising. However, it's actually much better. So the gap, so if you look at, say, SNR minus 15 dB, okay, then we're talking about a factor of almost 2.5 gain. Okay, so 2.5 gain, that's a lot. That's a lot of gain. If you transmit 1 megabits per second, you now get 2.5 megabits per second. Okay? All right? Number two, which is more surprising, is that this curve is actually greater than 1. Greater than 1 means what? Means that if I look at an AWGN channel, okay, with the same received SNR, with the same SNR, so let's say same transmit power budget, then the fading channel actually gives me better capacity than the AWGN capacity. So now this is the first evidence that, a fading channel may provide some opportunity for us. We're not losing performance anymore. So the point of view we always talk is that, look, fading is bad. We've got to do something about it. We've got to get back to the AWGN performance. So automatically in the mind of wireless engineer, the AWGN performance is kind of like the frontier. And you're always below the frontier. You always want to get there by essentially removing the fading, diversity, and so forth. But here is a case in which you're actually doing better than the AWGN channel. Okay, so let's see why. Let's understand why. Okay, so let's understand why. If I look at this curve, okay, at low SNR, we don't have the water up to the 4th floor anymore. So the water is now all the way down here. All the way down here. So now I have very small amount of water. Very precious amount of water. Okay? Where am I going to put it? Sorry? We're going to put in the best channel, right? We're going to put in the lowest points. Okay, so putting the best channel is not an optimal strategy in general. I talked about that already. Putting all the power in the best subchannel is not the optimal strategy in general. But the lowest scenario it is. Because I have so little, I might as well just put it in the best subchannel. Okay? And in the best subchannel, what is my channel strength there? The channel strength there is above average. So, therefore, I'm getting now a channel whose received SNR is actually above the average SNR that was seen by the AWGN channel. That's why I get better performance. So what's that picture? Okay, so what's the picture here? Is that I'm basically waiting for the peaks to happen. Whenever I see the peak, I transmit. Okay? So without fading, there are no valleys, but there are no peaks either. See, they come together, right? The fact that you have valleys also means you have peaks, because the valleys are the destructive interference points. The peaks are the constructive interference points. They come in pair. When you look at it from a slow fading situation, these valleys are very bad. When you look at it from a fast fading situation, you can code over the valleys, but if you now have CSI, the transmitter, as well, then you can track where the peaks are, and you can transmit at the peaks. And you get better performance. Okay? So we get a result here. Now, let's think about it from a system point of view. Okay? So I have this theoretical result, and now I want to think about how do I put this result to work, right? How do I make some buck out of this result? Okay? And suppose I take this result and I go to a wireless company and say, hey, you know what, I have this cool idea. You guys got to build this system. You know, it can give you like 3 times the capacity of AWGN channel, good stuff. And then they look at me and say, there's something wrong with this result. From a system point of view. Not from a mathematical point of view. There's nothing wrong with mathematics. From a system point of view, there's something wrong. Several things wrong. One, I'm operating at a regime where the spectral efficiency is low, because the SNR is low. So the bits per segment hertz is low. The carrier paid $1 billion to buy the 1.25 megahertz. I'm not going to operate at low spectral efficiency, man. I'm going to operate at as high spectral efficiency as I can. So therefore, I want a scheme which gains performance at the high spectral efficiency regime, not the low spectral efficiency regime. That's the second thing. That's the first thing. The second thing that is wrong with this result is that it assumes an average power constraint. Right? So what am I assuming here in this result? I'm assuming that I have a total amount of average power, of an average power constraint, and I want to use that power in a fruitful way. But in most communication systems, most cellular communication systems, I don't really have an average power constraint. In some sense, I have a peak power constraint. I want to keep I'm not essentially limited by, like, for example, the base station. It's not limited by power energy. It doesn't run out of batteries. It's always plugged to the wall, to the ground. Okay? So it always wants to transmit stuff. So this result essentially says that, no, when the channel is bad, save your power. I say, I don't want to save my power. I want to send anyway. So most of the time you want to send, and so the times in which you hit the peaks are rare. And so the gain is very small. So if you change the power to a peak power constraint, or something like that, then the gain is not very interesting. So the gain here is really coming from only the situation where you have a severe energy limitation. So imagine you have a sensor node, and you have a very severe energy limitation, and you want to use the energy very fruitfully. Then this may give you a gain. However, that sensor networks is not really, it's kind of researchy. It's not going to make you any money within a few years. Cellular communication is making the money. So now how am I going to convert this theoretical idea to an idea that I can implement in a real system, in a real cellular system? That is what I'm going to talk about in the next section. Okay.